Welcome to the second and last video for Lecture 3. In the first video, we talked about uncertainty analysis, and here we talk about calibration. Specifically, we will introduce a couple of concepts related to adjusting instrument and the procedures for calculating linear calibration curves using least squares-based procedure. One purpose of calibration is to define the relation between the physical change that a sensor or transducer senses and the sensor's output. Another purpose is to check the instrumentation system to confirm its accuracy. If the system is outside the desired accuracy tolerance, then either or both the sensitivity and zero offset may need to be adjusted. For this class, we will focus on the first purpose, which is to find the relation between physical change and the instrument output. Every sensor needs to be calibrated to find the relation between the physical change and the sensor output. For example, thermocouple with dissimilar metal junction generate a small electromotive force or voltage in response to the temperature sensed. A calibration curve is needed to relate the EMF, which is the electromotive force, to temperature. In real application, this relation is nonlinear. You will practice calibration of temperature sensors in the upcoming lab sessions. We will also use other sensors in lab where some physical change causes it to generate an output and measure. In some labs, we will want you to find the relationship or the calibration curve. Calibration curves can be linear, quadratic, power, or other nonlinear relation. For this class, we will mainly work on linear calibration curves. Here is a graph with a linear calibration line to be found the best fit for dataset X and Y, where X is the input span and Y is the output range. This is similar to the sensitivity graph. The equation of the best fit line is given by Y equals A times X plus B. Many electric instruments use linear relation between the sensed input and output. Several key terms include slope, which is the sensitivity, zero offset, which moves the entire curve up or down. When we adjust an instrument, we can usually adjust the sensitivity A and the zero offset B in a linear relation Y equals AX plus B. At several points in this course, you will be asked to generate calibration curves for some data you have collected during the lab exercises. You are going to use this linear calibration procedure. In the relation you are to develop with the data is in the form of Y equals A times X plus B as shown here, where Y is the sensor output and X is the actual input value. Find A at the slope, B the zero offset, and error mean square, which is SY square, and several standard deviations such as SA, SB, and SX. Let's use a pressure gauge sensor example in the course package. A dead weight tester can generate known pressures very accurately. It is commonly used to calibrate pressure sensors. We used to have a dead weight tester in the lab session, but we decided to discontinue it as we only have one and it is aged. In this example, we are going to use the dead weight tester to calibrate an electric pressure gauge with output in millivolts. What we want by the end of this procedure is to build the relation between the pressure gauge reading in millivolt and the real pressure in K pascal, given by the dead weight tester. And the relationship we are looking for is X equals alpha times Y plus beta. Note that this equation is different from what we introduced at the beginning of this session. We start by the original linear relation equation introduced earlier, with some typical least squares procedure, including finding a and b, calculating error mean square, sy square, and the standard deviations sa, sb, and sx. This example is on page 3-7 in the course packet. In this example, there are 22 data readings with a range of 0 to 10 kPa. 11 data points were obtained by adding more weight, and the other 11 points were obtained by removing weight. This is a way to test the hysteresis effect of the sensor, which we will talk in later class materials. The notes on page 3-7 and 3-8 in the course packet also give all necessary intermediate results for you to use, so you don't have to calculate them by yourself. In the end, we get the slope A as 1.08 millivolt per kPa, and the offset B as minus 0.85 millivolt. And we get the linear relation to be y equals 1.08x minus 0.85. But we are not done here. This slide shows us how to get the pressure reading from the voltage reading from the sensor. This is when we use the electric pressure gauge later on unknown pressure. We can reorganize the equation to get alpha and beta. So the calibration equation is x equals 0.926 times y plus 0.787. Let's assume that the reading error is small and follows Gaussian distribution. Then, statistically, the 99.7% uncertainty of the sensor output is given by plus minus 3 times Sx, which is one of the deviation, if you remember. Based on the notes, Sx equals Sy over A. In this case, it will be 0.19. Given the sensor reading Y equals 4.32 millivolt, we can calculate to get X to be equal to 4.79. And we calculate the uncertainty at 99.7% is 3 times of Sx, which gives us 0.57 kPa. Therefore, we get X equals 4.79 plus minus 0.57 kPa. This brings us to the end of Lecture 3, Section 2. We talked about calibration in this section. Again, please write down any questions you might have about this material and bring them to class for discussion. Thank you.